one of the important things we need to be able to do with functions is to determine their domains. Now, remember that the domain is the acceptable x values. That is, the numbers that you can substitute into the function and not have some kind of problem happen. Now, I've listed here the four primary things that you need to look for. Any function with a variable in the denominator will be undefined for numbers that make the denominator 0, so those numbers will have to be excluded from the domain. Since you can only take the square root or the logarithm of a positive number, the domains of those functions can only include numbers that make the expressions you're taking the square root or logarithm of positive. And finally, with piecewise defined functions, you have to look closely at the ranges where the function is defined to see if there are any gaps. So for the remainder of the lecture, we're going to look at specific examples of functions and see how their domains are defined. Now, this is, I think, the most basic example of situation 1 from the list, where we have a variable in the denominator. Here, the denominator is 0 when x equals 0. So we have to exclude that value from the domain. In other words, the domain is going to be all real numbers except 0. Now, there are three ways that we can write this. One is using the set builder notation. D equals the set of all real numbers such that x is not equal to 0. The second is using the interval notation. Now, I use parentheses on the two parts with the 0 to indicate that 0 isn't included in the results. And the u in the middle means that we're taking the union of the two individual sets. And the last method is the set notation. All real numbers except the set 0. Now, which method you use for a given function is mostly personal preference. For something like this, where we just have to exclude one number, personally, I prefer the set notation because it's the most compact of the three, but all of them would be acceptable answers. Now, this example is similar to the previous one, with variables in the denominator, but with a more complex expression. The procedure here is the same. We need to find the values that make the denominator equal to 0 and take them out of the domain. That means solving the equation x squared minus 2x minus 3 equals 0, which we can do by factoring. Now, notice I'm going to write not equals here rather than equals. That's a reminder, that we're finding the values that aren't in the domain. So next, I'll set the two factors not equal to 0. And solving these equations give us the two values that we need to exclude. X can't equal -1, and it can't equal 3. So our final answer will be that the domain equals all real numbers, except for those two. Using the set builder notation, that would be D equals the set of all real numbers such that x is not equal to -1 and 3. Using the interval notation, we would have this. And finally, using the set notation. Now, you can see, I think, even more here, why I prefer the set notation for situations like this. Removing 2 points was much simpler and clearer that way than writing out multiple intervals like you have to do using the interval notation. Now, when we're working with square roots, or really any even root, we can't put any value in for x that makes the expression under the square root negative. So for this function, that means 2 minus x has to be greater than or equal to 0. And solving this inequality gives us x has to be less than or equal to 2. Now, in this case, remember, we were solving for the good values, right? Unlike the last two examples where we were looking for the numbers that had to be excluded. That makes the domain the set of all real numbers such that x is less than or equal to 2, or the interval from negative infinity up to 2. Now, notice how I use a square bracket here by the 2, right? The original inequality was less than or equal to. So I use a square bracket to indicate that 2 is going to be part of the final interval. Now, logarithms are similar to even roots, where you can't have any value in the domain that makes the expression you're taking the logarithm of less than 0. So for our function, that means we have to have x minus 5 is greater than 0, or x is greater than 5. And notice that I used strictly greater than here, because you can't take the logarithm of 0. Now, using the set builder notation, that would give us the set of all real numbers such that x is greater than 5. And using the interval notation, this would be, and here we would use parentheses by the 5 to indicate that that isn't going to be included in the final result. All right, now when we're looking at piecewise defined functions, there are actually multiple things we have to consider. First, we have to think about items 1 through 3 on our list from the beginning of the lecture. Do any of the expressions have variables in the denominator, or even roots, or logarithms? Our two expressions here are x minus 1 and x squared minus 3. None of those issues appear here, right? So we don't have to worry about those items. Now, finally, take a close look at the two intervals. Right? And notice that 2 isn't included in either of them. We have strictly greater than and strictly less than. So that means the function isn't defined for x equals 2, so that won't be part of the domain. With the set builder notation, that would be this, and with the interval notation, it would be this. And finally, with the set notation, you would end up with this. All right, so that's our last example for this lecture. In the second lecture in this series, we're going to take a look at some more examples, some more specific functions, but kind of ones that have more complex situations. For example, ones where that combine the criteria we have to look for, like, for example, a function that has both a logarithm and a variable in the denominator.